is a fellow of the AGU and has received both a Maselway Medal and given his Turco lectureship. And today she's going to tell us about explainable AI for climate.
Thank you. Okay. First I want to make sure everybody's aware I sound like a frog, but I feel fine. So don't worry, I'm okay. All right. So I'm a climate scientist by training, but I've really started working in the field of explainable AI and climate the past 5 or 6 years. Because of that, I framed this talk really about the climate science and how I use AI on a daily basis in hopes that by the end of this talk, there are things hopefully this audience can come up and chat with me about afterwards. So it's sort of the day in the life, if you will, of what we think about. All right, let's see. Perfect. So we have a challenging future ahead of us. First, the Earth system is threatened. Global environmental change, both carbon dioxide going up into the atmosphere, but also changes to the land surface are really unprecedented. And with this, we're starting to see people being impacted and seeking to escape from worsening climate hazards. So this is both an environmental, a physics, physical climate system problem, and a people problem right together in this complex system. And so what's really motivating the work that we do is thinking about anticipating what's to come. This could be what's going to happen tomorrow, what's going to happen 5 years, 10 years, 100 years from now. Can we understand and inform society as we navigate this future? So I first want to start off with how I think of AI, and that's as a climate scientist, I've just got a really big tool belt, and I see machine learning as just one of the tools. Sometimes it's a terrible idea to use the hammer when you're trying to put in a screw, and other times it's just the right tool for the job. And that's how I really have, I think, been able to communicate with many of my colleagues who are not AI people, is reminding them it's not here to take over all of their jobs or all of climate science, but really is there as a tool to help them do it better or faster. Next, I want to point out that AI for climate is not new. You go back in the literature, you will find a paper from 1964 with a very, very simple neural network designed specifically for weather prediction. So with that said, of course, the field's interest has truly exploded in recent years. One of the reasons for that is we have so much data. Not all of it's great data, but we have so much of it. Be it space-work observations, reanalyses, so sort of observation/model products, as well as climate models, as we heard from Gavin in the previous talk. And already, one of the things we do as climate scientists is we look to the commercial sector, we find a cool model that they've trained, and we see what it can do for us in climate. This is one of my favorite examples of creativity being key. So colleagues saw this in video a few years ago showing an infilling of an image, and they said, well, that looks a lot like temperature reconstruction. So going back into the 1800s to see if we can fill in gaps in our observational record where the ships, for example, were not traversing and taking measurements. And in fact, they show that there are many reconstruction methods out there, to be clear, but this is yet another way of doing this problem. And they show that actually they have evidence from their AI reconstructed record of the reported El Nino from 1877, which we know occurred due to written records, but most reconstructions cannot get correct. So there are many AI applications to date in weather and climate. Here's just a few. Pure weather predictions. So just as Gavin already mentioned at the end, pure data-driven weather prediction. Convective parameterizations and climate models. There's a lot of effort right now going into improving these parameterizations specifically to make better and faster climate models. Downscaling. Again, this has to do with the fact that people don't live in a 100-kilometer grid box. They live at a point, if you will, and they want to know if it's going to rain here, not the average rain, say, in their state. And finally, one of my favorites that I actually think is really compelling when you're talking about climate change, and Gavin touched on this too, is the communication side. And I find it incredibly powerful to be able to go to a website and pull up a street view of my house and see what it looks like under, 2 feet of sea level rise, for example. Well, in Colorado, 2 feet of sea level rise isn't really a problem, but along the coastline, this might be a nice tool. They also sadly will show you images of your house on fire, which is much more of a scary thing for us in the Front Range. So in my goal, as a climate scientist working in AI, is to develop and implement AI tools to leverage our imperfect climate models in support of Earth system prediction across time and space. That's my very, very lofty goal. And climate models provide an inaccurate, but in my view, invaluable parallel universe, set of parallel universes that we can mine for information. And so I sort of think of these as lots of different worlds that we will never ever live in, but maybe across them we can start to learn connections and behaviors and things about the climate system we didn't know before. So I want to go through some examples on timescales of how we're using AI to try and achieve this goal. I'm going to start with long time scales, thinking out decades, and then come to multi-year, so over the next few years, and then sort of end with sub-seasonal, so 2 weeks to 2 months. That's sort of the overview here. So for a while now, we've been talking a lot about certain critical warming thresholds and when will we actually reach those thresholds. So the world at 1.5 or the world at 2 degrees C above pre-industrial levels means different things for different ecosystems. And the question is, when will we reach these particular levels? When will our observed Earth? Now, one of the problems is, we've already seen this, many different climate models, as shown by these different colored lines, have different timings of when we will hit these different thresholds, as shown by the dashed line. But also these different thresholds are dependent on what scenario we follow. And we already know we're not on any one of these exact scenarios anyway. So the question is, can we still learn information from the data we have, knowing that none of these lines could possibly be us? So what we're doing is we're training neural networks to take in maps, annual mean maps of surface temperature. So think of the year you were born, you don't have to share it. Think of the annual mean map of surface temperature. It might look something like this. We train a neural network to take that map and tell us how many more years until that temperature threshold is met. Now we're doing this with climate model data because we have a lot of it and we know the right answer. We know how many years until that temperature is met. Now we're doing more than just predicting the number of years. We're actually predicting conditional distribution in order to get a range of uncertainties as well. So when we look at how it does on our withheld testing data, so climate models that we withheld that the network never saw during training, it does quite well when we feed it data over a range of years, asking how many years until you reach the threshold. But ultimately, we already know the right answer from our climate models of when that temperature threshold will be met. We really want to know the answer to this for the observations. And so once this model is trained, we can then go in and push through the actual 1980 or 1992 or 2021 map and ask how many years does the AI think it will be until that temperature threshold is met. All right, so first of all, we pushed these years through the model trained for a particular scenario. This is SSP7, and ask how many years until the 2 degree threshold is met. Now we do this because we have maps for every year going back to the 1980s. We can do this for every year and get a prediction. One thing we do is we're checking for consistency to make sure that this isn't completely out to lunch. So one thing we look for is every year that goes by, if this is working, it should think we're 1 year closer to that particular threshold. And in fact, we do see a slope of about -1, so that gives us some confidence. One interesting thing, you see that blip there, anybody already thinking like, I don't know about that 1 degree slope. That's Pinatubo going on. So this shows that the AI has not learned about volcanic eruptions. It's learning something much more general than that. So when Pinatubo went off, it was a huge tropical eruption. The globe started to cool slightly. And because of that, the AI thinks, oh, we must be further from that temperature threshold than I initially thought. And so it predicts a longer time. Now, volcanic eruptions and their effects take about 1 to 2 years to go away. And that's why we get back onto that line once again. This actually, believe it or not, makes me feel better. It's because it makes me see what it's learning and also what it's not. We can focus in on that final year. So when we wrote this paper, we had a 2021 map, and we can look at that uncertainty associated with the prediction of the time to 2 degree threshold. And one of the interesting things about these results is even under the low scenario, so that's the blue line of SSP 126, it suggests an earlier or a possibility of actually still hitting 2 degrees. Although I want to be clear, it's not we're not completely ruling out the possibility that it's avoided. And I can talk more about this if you'd like. But the idea here is trying to use AI to take a bunch of climate model data that doesn't agree and try to find consistent patterns that are also relevant to the real world. So thinking again about these time to certain temperature thresholds, let's talk about surface temperature or trends over the next 30 years or so. So what these maps are showing are all maps from the same climate model simulation, the NCAR model, but they're all started with slightly different initial conditions in the year 1850. So if you will, this is the butterfly effect. Starting off, the initial conditions are ever so slightly different. It's actually 10 to the minus 14th Kelvin different. So we're talking tiny differences in how they start. But very quickly, their climates evolve differently and their atmospheric, their weather evolves differently because of that chaos and noise. But when you look at all of these 100 different versions of what the future might hold under this model, you probably agree with me, they all look sort of the same. They're all red. It means it's getting hotter. Okay, so the climate change is happening. But if we focus on only 2021 to 2030, so not the next 9 years, you start to see huge differences across those different worlds. And what we're seeing here is natural variability or weather that is not part of that climate change signal. This is just the noise of the climate change system. And I think it's incredibly important to stress that natural variability on timescales of even 10 or 20 years can overwhelm that climate change signal, especially on regional scales. So when people are planning for the future, especially over the next 10, 20 years, thinking regionally, this natural variability is going to be absolutely critical in what they're going to see. So put another way, take a single point. I chose Chicago. All right, so this is Chicago over one particular climate model, 100 different gray lines on here, 100 different worlds or parallel universes we could be living in. Okay, they all go up. That's climate change. That's that force signal. There's lots of different wiggles, but that's weather. That's that weather or internal climate variability. So again, if you take the mean, we call this the forced response. That's that part due to things like volcanic eruptions and CO2 going up. And it looks probably like you'd expect. But you can instead choose a different world or ensemble number. This is number 40. And this is a world we could be living in. Or we could choose world number 32 and we could see something very, very different. Now, on the long time scales, it all gets hotter. So there's not much of a question. And that's really the work I was just showing you, talking about better constraining future projections. And that's largely what I think Gavin was talking about during this talk. But we can also focus in on shorter timescales, and you'll see that the gray line and the purple lines here start to look the same. That is, the natural variability tends to be a big part then of what it is we're looking at over this time period. And so one thing that we're doing in our group is really using AI to explore Earth system predictability weeks to years in advance. What can we say about the next 1 year, 5 years, or 10 years? And what part of that is the climate change signal and what part of that is that internal climate noise? And furthermore, you can focus in on a given year and ask about subseasonal to seasonal prediction, or what we call S2S, which is what's going to happen in the next, say, 2 weeks to 2 months. But hold on. Yeah, I would argue Gavin gave a somewhat pessimistic view of this. Climate prediction is really hard. So, and this is, I think, maybe where I think actually, Gavin, I'm going to put you on the spot. I think we might actually agree. This is a really hard problem. And I think expecting to make perfect predictions all the time is completely bogus. And anybody that tells you they can is wrong. But one of the things we're trying to do is bring physics into the problem and say there are certain states of the climate system, certain boundary conditions when there actually might be a predictable signal there. So instead, we have to look for these states, or what we're calling forecasts of opportunity, when we might have enhanced predictable behavior. One picture of that, this is something a few years ago, I said, I want to train AI to do this. Imagine that we have our data, it's all these black dots. 80% of the data is just noise. We're never going to predict it. It's not going to happen. Okay, maybe only 20% of the data actually lies along a nice line here. And if you tried to train one model to predict the whole thing or fit a line through it, it'd be a mess. So the idea is, how can we try and focus on that 20% of the data that's the signal while ignoring the 80% that's noise? And I would argue that in many AI architectures, I think impossible predictions are hampering its ability to learn that nice line here. And so what we're trying to do is use AI to find these particular states of the climate system that might lead to more predictable behavior. For example, we know the Madden-Julian oscillation, which is a region of convection that moves eastward from across the tropical Pacific and Indian Ocean through the tropical Pacific, can lead to predictable behavior in the latitudes weeks in advance. And we've already heard also about the El Nino Southern Oscillation, which drives to some extent precipitation and temperature anomalies throughout the globe. So how can we have AI help us find these, but also find maybe cases we didn't know existed in the first place? So as an example, Francis Davenport, a postdoc in my group, is thinking about trying to predict ocean temperatures 5 years in advance. One important point here is we're using climate model data to do this because we have a lot of it. So she's putting in past sea surface temperatures because we know the evolution, if you will, the DT is important in this problem. And so we input those into a CNN and predict at a certain grid point whether the average 5-year temperature in the coming years will be hotter, average, or colder than it is normally. So she trained this, and I want to point out, I don't have a pointer, but this is trained on the MPI or system model on 3,630 years of data. That's a lot more than we have in the observational record. So the idea of trying to do this without observations alone, I think is never going to happen. This is where we're really leveraging the climate model up. So she's having it do a 3-class problem. So random chance, the way she has this set up, is 33% accuracy, right? You just guess everyone individually. And if you look at the color bar, you'll see that it's worryingly close to the colors you see in the map. This is the point that this is a really hard problem. So if we were to stop here, we'd say, I guess we can't do this, even with 3,000 years of data. However, the whole idea here is to leverage this forecast of opportunity, which ultimately comes from understanding the physics of the climate system. And says, we ask, when the AI is most confident, is it also more accurate? The answer is yes. It's identifying opportunities for skillful predictions. So if instead we only take the 40% most confident predictions, we start to see skill that's much better than random chance. And if we take the 20% most confident predictions, pretty clear that the algorithm has learned these forecasts of opportunity when skillful predictions are possible. Well, this is again the MPI climate model. So if all you want to do is predict MPI, you're good to go. But we again want to know something about the real world, about the observations. I'll talk a bit about transfer learning at the end, but for right now, we thought, let's just see how this does with observed maps. We have observed maps that over the observational record. Let's put those in and see how it does. So again, if we look at the overall accuracy, it's pretty much random chance. But if we look at when the AI is most confident in its prediction, we see that there are accurate regions of the globe that we can now try and understand what's going on there. All right, but wait, I said explainable in my title. Don't worry, I remember. How is the network making its predictions? Remember, I'm a scientist here, so I'm not just a forecaster. So ultimately, I want to learn which regions of the globe are most relevant for each prediction so I can start to understand the physics and the dynamics going on in this climate system. So opening the black box is, a phrase we hear all the time, and explainable AI is certainly making huge progress. It's a bit of a mess, I would argue right now. There are papers coming out every week or so from computer science on different explainability techniques. And honestly, a big contribution I think that we've been trying to do is communicate these advances, albeit years later, with a year lag or so, to our community who may not speak the language of computer science. And so how can we use these explainability methods to do atmospheric and climate science? So there are a lot of XAI methods out there, and I'm happy to talk during a coffee break about them, but my favorite are attribution methods. And the reason is this is how climate scientists think already. They were very intuitive to incorporate into our workflow. So let me give you an example of how these attribution methods work. Let's say we've already trained a network to predict whether there's a cat in an image. This is a computer science problem. There are cats everywhere, you can tell. So we input a map of the cat, and it says, the probability of there being a cat's 0.8. It's really nice. Where did 0.8 come from? Attribution methods take that 0.8, propagate it back to the network, and ultimately create a heat map of the same form as your input, highlighting the regions of the input that were most relevant to the prediction. Some of these methods even have conservation principles, whereas if you add all the attributions up, you'll get out a 0.8 at the end. So this is telling us that the network used the pixels where there is a cat to determine if there is a cat. Maybe not super insightful, but you get the whole point. Now, if you've seen me give a talk, this is my favorite set of slides of all time. I did not make them, I can take no credit. But here's an example of how we can use XAI to identify problematic strategies in our network. So they've trained an algorithm to determine if there's a horse in the image. And I know these are blurry, but if you squint, hopefully you can agree there are horses in both sets. And then they apply these attribution methods. And the red regions are the regions that are most relevant to the prediction. And you can sort of argue the reds might align with horse bits. Okay, all right, so far so good. So 3 more pictures of horses. The AI also said there were horses in each of these images. Where did it look? And when we look at this, the region that's most relevant is not where the horse is, but it's the copyright symbol. And the reason is this particular algorithm was scraping images off the web to learn during training. And most of the horse images came from the same German website that always had the same copyright symbol. Now, on the one hand, maybe this is okay with you as a scientist, this is not okay, because I'm trying to learn something more than the copyright symbol here. And so in this way, these tools can be really helpful to identify these problematic strategies. Now, I've given those slides before, and I've had people say, hey, you're a nerd scientist, you care about why. I don't care about why, I just want to make really good forecasts. But I still would argue, if you don't care about why, you still need to care about XAI. One of the main reasons is to gauge trust in your system, to actually believe it's giving you the right answers for the right reasons. I would argue this is incredibly important, especially for weather prediction and weather forecasting, where lives are at stake. Another thing that we've used it a lot for is fine-tuning and optimizing our algorithms. And this is really important, I think, for AI plus science. As scientists, we already have knowledge. Sometimes we try to put it into the network. We're going to be talking about that, I'm sure, over the next few days. But sometimes it's still external. And this is a way of saying, hey, I know this information is important. Has my network figured that out yet? And if not, maybe I can tweak the architecture to make it learn that better. And finally, I am the nerd scientist, so learning new science is certainly important to me. Although I will point out my ultimate goal here is to understand causality. And XAI does not give us causality. It's still a correlation causation issue, but I would argue it's a step in the right direction. Okay. So how are we using XAI for these problems? This is an example very similar to the one I just showed you, where we're predicting the 5-year average surface temperature at each grid point, inputting lagged sea surface temperature maps to predict whether the temperatures at a certain point will be above or below normal in the coming years. This again is trained on climate model data. This is over 1,000 years of data. Once we've made the prediction, we can then use explainable AI to make these heat maps of the most relevant regions for the network's prediction. So in predicting for Mexico, California, the Midwest, and Canada, we get different heat maps or different regions of the globe that are important for that prediction. When we see things that maybe we would expect, like the Kuroshio extension, for the Midwest, we see that El Nino Southern Oscillation anomaly there, but it really starts to highlight regions of the globe where there are sources of predictability that maybe we need to leverage. But also because machine learning is nonlinear, right? For the same prediction, we can learn different sources of predictability depending on those boundary value problem, the boundary at the beginning of the prediction. So for example, in predicting for the US West Coast, some of the samples, the most relevant region was again, the Kuroshio extension, whereas for others, it was actually Atlantic. And this is something, again, now in this case, we're learning from the climate model only, and a step is going to be making it relevant for the observations as well, where we have much less data. So that's our thinking about the next or multi-year prediction. But what about an even higher time scale? So sub-seasonal to seasonal prediction. This has been really important the last few weeks for like atmospheric river activity hitting the West Coast. And the question is, or for reservoir management, the question being, if we can give them reservoir managers a heads up before these events occur, maybe they can weigh the risks and benefits of letting water out of their reservoirs a little bit earlier. So this is work done by Mary Beth and Arcodia and my group, and her focus now is predicting precipitation 3 to 4 weeks later. I will point out this is not a deterministic prediction. This is at these timescales beyond about 12 days or so. We're talking about probabilities here. And again, this is part of that chaos taking over. So if we're trying to predict precipitation 3 to 4 weeks later, in this case, I'll show you some results for California. And what our input is maps of tropical precipitation. Now you might say, why the tropics? Well, it turns out we know from physics that the tropics are one of the leading sources of predictability for mid-latitude weather in the coming weeks. And so we use that as an input. So when she gets her results, the way she set this up is predicting above or below average rain. So a 50-50 chance is random chance. Okay, a 50-50 shot. So if you look at all predictions, those colored bars or those colored lines are pretty darn close to 50%, which once again shows this is a really hard problem. We're not doing so well. But again, if we use the AI's ability to find these forecasts of opportunity, we find that when the network is more confident, we do have higher skill. So again, accuracy is increasing with confidence. We can then ask, well, what is it looking at to find these forecasts of opportunity? And we can use XAI to go back and make these heat maps. And what we see is both regions in the tropical Central Pacific as well as the Indian Ocean. And these are largely picking up on that Madden-Julian oscillation and the ENSO piece of information that we know already is important. Now you might say, well, we knew those were important already. Fair point. However, I will point out most predictions or many predictions using ENSO and the Madden-Julian oscillation have consolidated them into a single index. And at the end of the day, it's not the entire phenomena or pattern that's necessarily important, but particular pieces or parts of that pattern that actually drive predictability into the latitudes. And AI is helping us identify those exact regions of the globe that are most important. Furthermore, Mary Beth took this model, trained, by the way, on 800 years of climate model data, and once again said, what happens if I put observations in? So this is for actually observed maps and predictions based on observations for California. And a few things to note. First, you'll see that that our accuracy is far above random chance. I don't have a line here, but it is. And secondly, and this is really the focus of this work, is showing that there's variability in this accuracy. Some decades, we may actually be able to leverage these forecasts of opportunity better than others and try and understand the climate dynamics for why that is. And lastly, in this set of applications, I want to point out something that I think is pretty special about this approach, which is asking the question, do we expect predictability to change as the climate continues to warm? Running climate models already is really computationally intensive, but running them in forecasting mode in 2050 is not going to happen. I asked these CMWF ones if they would do that for me. They said no. So instead, what we can do is train AI to be our forecast model and apply it in the present day and in the future climate with our climate models and look at how those sources of predictability change. So this is work done by former PhD student Kirsten Mayer, and she has a similar setup as before, but she's predicting the jet stream over the Pacific. And what we see again is if we look at all of our predictions, they don't look different between a historical and future climate. It isn't until we really focus on those forecasts of opportunity that we see big changes in predictability in the coming years. And we can use XAI to say where are those changes coming from. And they're largely coming from changes in the contribution of El Nino to what's going on in the latitudes. And we can see that by that diminishing importance of the El Nino region in a warmer climate. Okay, good. So I just want to move to where I am excited about going here. So personally, Explainable AI has been really interesting and exciting, but it still sort of feels like I'm explaining a black box from the outside. And so there's a lot of work now on thinking about interpretable models that are interpretable by design. So XAI tells us where, but not how. So this is a great review paper if you're interested in the topic, saying, evidence of an animal being a Siberian husky, and it looks at where the husky is, but also evidence for the animal being a flute, and it also looks at where the husky is. And so XAI is not going to solve all of our problems. So can we build interpretable models from the get-go? All right, so that's really my current goal, is to mimic scientific human reasoning, how a climate scientist would do the problem and try to build AI models that can do that for us. Just as an example, this is some work that came out of the computer science community a few years ago, titled "This Looks Like That," saying, how do humans identify what type of bird they're looking at? They'll say, hey, look at that head. That looks a lot like a head of a bird I saw a few weeks ago, and that was this kind of bird. or that was this kind of sparrow. Oh, look at its feet. Its feet look like this other kind of bird, this other picture of a bird I saw a few years ago, and it was also a sparrow. Maybe this is a sparrow. So this type of thinking is great. I really like this. But when I read this paper, I said, that's awesome for pictures of birds, but this is not how the climate system works. Put another way, this is saying this looks like that anywhere. But really in climate, it's really, this looks like that there. It has to, having a high pressure system in the Pacific versus the Atlantic is a very different weather setup. And if for those here that are more on the computer science side, this is really getting to attention or attention networks. And so we've now developed this model further to help us identify things like that Madden-Julian oscillation, but specifically finding these prototypes that are location specific. Okay, so this is my last section and I'll wrap up here. So the Earth system over the last few talks, hopefully we convince you it's complicated, it's coupled, it's complex, but humans are a part of this, right? Human development and environmental factors cannot be easily decoupled. As a climate hazard occurs, people respond, they may move and develop elsewhere. And so one of the big questions that I'm really interested in moving forward is, and in finding collaborators, is can we quantify the present and anticipate future changes in human development under climate drivers and impacts? And so just as an example of a flavor of the work we've started is thinking about human building an AI-based human footprint map to quantify the effects of humans on every pixel of the land surface. Now, the only reason we've been able to train this network based on Landsat imagery alone is that a group of people, Williams et al. 2020, already spent 7 years doing this and labeling the data for us, using a range of data sets to come up with this index. Once they came up with that index, though, we were able to then train a neural network to take in Landsat imagery alone and predict this quantity, this value between 0 and 1. So here's our AI-based map for the year 2000. And we then, in a matter of minutes, could do the same thing for 2019 or 2020 or 2021, whenever we have Landsat imagery. And then we can go and look at changes. And just this is one of my favorite examples. The Landsat imagery is on the left from the year 2000. And in 2019, that's the middle panel. And the right is XAI, highlighting why the AI thought the human footprint doubled over this period. And what you see is it's really highlighting that highway that went in, and actually that's the Trans-Sumatran Highway that went in 2019, showing how important it is to keep these up to date and have up-to-date methods that can be easily implemented. So we did that for a range of places on the globe, identifying different land use changes. And of course, land use change and AI has been a focus for years. Our particular focus, though, is this single index is trying to then link it to climate drivers, for example, landslides, and better understand how humans respond to these particular climate events. And so that's some of our focus over the next few years of work. So this is my final slide. I want to point out some other additional new frontiers that we're interested in. Transfer learning. So far, I've only showed you results where we took the AI model, trained on climate models, and said, hope it works, and then put in observations. Okay, there are certainly going to be times it doesn't work at all. And how can we leverage the observational data sets that we have? So this is one area of that's really, I think, important. And to me, one of the more exciting avenues forward is leveraging these imperfect climate models with transfer learning. Another area of work I haven't talked about is using many of these methods to understand the potential impacts and future scenarios under solar climate intervention or geoengineering. And we have quite a bit of work going on using these to identify patterns of change or impact due to these, and to simulate a range of scenarios that we couldn't, where we could only typically simulate a few. And finally, linking back to this human piece, anticipating these cascading crises of climate events, where a climate event when one location on the globe no longer stays there, but really propagates throughout society. Can we start to better understand and quantify those interactions? So with that, I will end, and thank you.
Thank you. This is a very good talk. A lot of idea coming from this talk. Actually, I have two questions. The first one is so you have two kind of prediction in your talk. One is like season to seasonal, like the next couple of weeks, and that is very like long year, like more than 10 years, 20 years. Now, when you do those, are those two models different in structure by nature, or they are kind of similar, you're just training them with different data? That's the first question. The second question is regarding to the data. I understand that you train them by using different data set, but do you have like a different frequency of the data in different for this training? Because the frequency of data will determine what of the treated as noise, like how to treat those. Those are two questions I have. Thank you.
Yeah, so I'll take the second question first. So yeah, so we have data at very different frequencies. So climate models output data sometimes up to at 6 hourly increments. And so in some of the examples I showed, we don't need 6 hourly data to do a 5-year prediction. And so in that sense, sometimes we will annually average, so we'll make it yearly data. And so we'll have one sample per year. So that all is the scientist deciding what is the best, the cost benefit of having higher frequency data, but also takes longer to train, data storage is an issue, etc. So that's a decision that we make. Your first question, is it sort of the same architecture? Right now, generally, we use the same architecture because we found we can make pretty good inroads, even with relatively simple architectures. A big issue here, though, with everybody is overfitting, but we're hearing about millions of samples or billions of samples, and we have, sometimes only 1,000, sometimes 100. And so oftentimes the simpler the architecture, the better, in order to actually find something useful in this noise. With that said, there's a lot still to explore, but and as I said in my interpretable model, we're actually trying to design models that go even a different way and say by design are designed for the task at hand.
Hi, that was a really fascinating talk. I was just curious, one of the barriers in many applied domains is sort of easy access to data, and this is so multidimensional and so complicated. I'm just wondering, what are maybe it's for you and the previous speaker, in climate science, what are the efforts being made to make data more accessible, more like easily approachable for not just specialists, but machine learning scientists, high schoolers, undergrads, how can that be potentially improved?
I'm going to let Gavin also respond. So Gavin, be ready. So this is a huge issue and a big area, and people have been talking about this, I would argue, for a very long time, and I don't think we've figured out how to do it right yet. You're talking about high schoolers. What about us poor climate scientists can't figure out how to get the data? This stuff is hard, especially we heard satellite observations earlier. That's a whole different can of worms with their different levels of processing. People are very aware of this. I don't have any good answer though. Right now, I think Gavin already mentioned, every group now mostly has a commitment to open science, but if everybody's doing their open science and open data in their own local repositories, it's still really hard to access. So I'm not sure I have a great answer other than it's a struggle. Gavin, I'm sure you have some more to say.
Yeah, just very, so all of the CNIT data is publicly available, but it's about, like 10 petabytes of data. And so, like searching through it in intelligent ways on its native area is impossible. So a large chunk of that, about a petabyte of that, has been put onto the Amazon Web Services East, maybe. Through the Pangeo project that's run by Ryan Abernathy at Columbia, Dex at Columbia. And that's so if you want to do like kind of Jupyter network, Jupyter notebooks and things, then you can bring it in and do lots of things. It's not complete, but it's much better. In terms of things like the satellite data, this is something that NASA is very concerned with, mostly because NASA spends an enormous amount of money putting things into space and spends almost no money in making it available to people, and then they wonder why nobody uses it. That's a perennial issue, but we're working quite hard. There's a project called the Earth Information System, where we've done some prototypes where effectively we're putting all of that data into the cloud, making it into cloud friendly formats again, so that you can search through it and build applications from it in a much more intuitive way and accessible way. But we're a long way away from being able to say, hey, give me the prediction for this from this model from blah, 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 and then it just gives it to you. So, but I think there's scope there.
Hi, fascinating talk, David Miller, University of Chicago in physics. And of course, so I loved how many times you referred to, the knowledge base that goes into some of the climate models from physics. And I also loved the section of your talk where you highlighted, this looks like that there. And I must imagine that there are well-known reasons why this looks like that there, as you pointed out. And to what extent do you embed that information from a fundamental perspective? We're going to hear a lot this week on other applications embedding symmetries, people sitting next to me in various models. And you didn't go into a lot of detail into what you're doing in that regard, but it sounded like there was a lot of meat on that bone. And I was just curious if you could expand on it in this context, because it sounds fascinating.
Yeah, so if I understand your question, in terms of interpretable models, the idea being, the head of the bird or the feet of the bird. So one of the things that I was really interested in is I've seen lots of other networks where you already say, well, I know the head's important and the feet are important. Find a way to connect those to my prediction. That was not what we were interested in here. Part of my point is always looking for sources of predictability that we don't know exist. So if I already knew that this particular region was important at a certain time, I wouldn't be learning anything new. So this setup at least was designed to help us find the there and the that. So it's actually learning, instead of us embedding that information ourselves, it's actually learning those regions that we should be focusing on and when we should be focusing on them. If that answers your question. And what I like about, sorry. Right.
Exactly.
Yeah. So a lot of people
Thank you.
bring up imposing conservation laws. I think this is one of the things that got me so excited when I started thinking about physics and AI. There are some great examples, especially for cloud parameterizations, where certain conservation laws like conservation of energy or mass are really easily implemented. Sort of when you sum up the column, the bottom column has to give you the total that you know from energy conservation. When we get to the work that I'm showing here, people from outside the field say, oh, put in conservation of mass. How? We're not going to be integrating the whole globe every second of a simulation that I didn't run, by the way, where I only have daily or monthly or annual mean data. So actually embedding this physics, if you're talking or bringing in conservation laws, I'm not even sure what I'm conserving here. So that is why when people bring up pins or, physics informed neural networks, I actually get a fluffier, fuzzier version of that where I say I'm using physics in my forecast of opportunity approach, or I'm using physics in how I designed the prediction problem with the tropics informing on the mid-latitudes, because I'm having after 5 years of thinking about it, I still have not figured out how to bring in those fundamental laws to this problem in a way they're brought in the climate models themselves, to be honest. Yeah, I'm sorry. I would love to have a better answer for you.
Thank you. I really like the talk. I have two questions. First, when we talk about 1,000 parallel universe, are they different models, the training on subset of the training data, like which kind of distribution are you drawing from? The second question is, when you talk about confidence, how do we model confidence? What mean in what sense is a confidence interval or something?
Yeah, so was your first question about the different climate models and are we training on all of them? Is that what you asked?
Yes. So when we talk about all this 1,000 universe,
Yeah. In essence, that's what we're doing. So all the climate models, many of the climate models have different physics where the physics isn't super well known. And so they all simulate the world a little bit differently. In some cases, we train on one climate model at a time to try and best learn that universe alone. And in other cases, we pool them together with the argument that places where all of those climate models agree might actually be rooted in reality, if you will. That's sometimes a good assumption and sometimes not. Is that okay? And then the second question was confidence. Great question. I did not talk about that at all. So do I have a whole other area where obviously statistics becomes incredibly important? What do we even mean by confidence? In some cases, we are actually doing, we're using more statistical based methods to predict a conditional probability distribution, using, for example, a log likelihood estimation. In other cases, we're using the output from a softmax and saying it doesn't have to actually be tied to reality and statistics, but the higher number wins. And this is where I really think that the statistics side can really help inform that end of the pipeline, especially because I think this confidence matters and is important. Certainly when we take it to go to risk analysis, et cetera, we need to make sure it's calibrated, et cetera. So different examples I showed, we do it in different ways.
Thank you.
Thank you.
Really great talk. Thank you so much. One thing I'm kind of curious about thinking of like explainable AI in climate science is if there's any work been done that you're aware of that's like trying to use or connect explainability to like opportunities for interventions or like places we might be able to, you know, actually do something and make a big difference in kind of guiding those efforts.
Yeah, so in the weather communities, I don't know the acronym, maybe they call these like Aussies. Like, can you identify the regions where had you had more information or focus there, that would actually have improved your prediction later on? So when I write a proposal, I say things like, knowing the sources of predictability can help us know regions where we need to have better observations on the ground. With that said, I am not aware of any papers that have actually gone and quantified certain examples, but I think in our work on solar climate intervention, for example, we're trying to identify the places that seem most sensitive. And that has gotten some interest in, does that mean we need to be monitoring those locations more than other locations? So great idea. I don't know the exact examples, but I'm sure they're out there, but moreover, I bet you they're coming.
Okay, let's thank the